So we discussed enough about electrostatics, that is electric flux density, electric field intensity, like that. So now we will be going through the basics of magnetostatics, and for this in our syllabus you don't have to learn much about magnetostatics, but still we can just go through the basics of it and learn the Maxwell's equations. Okay, so first what you have to learn is Ampere's circuit law. It states that the line integral of the tangential component of H around a closed path is same as the net current I enclosed by the path. So this is the equation form. It will be much easier to understand. Line integral of H dot dl will be equal to I enclosed. Here I is the net current enclosed by the path and H is magnetic field intensity. Like we can compare E in electrostatics with H. E and H, that is electric field intensity is E. Similarly here H will be magnetic field intensity. Okay. And applying Stokes theorem, you can convert that line integral to surface integral. So you can write surface integral of del cross H dot ds will be equal to, again I can be written as surface integral of j dot ds, where j will be current density. So both left and right is in surface integral form, and you can equate as del cross h is equal to j. Okay, so first Ampere's circuit law states that line integral of H dot dl is equal to I enclosed. On applying Stokes theorem, you will get del cross H or curl H is equal to J. Here H is magnetic field intensity and J will be current density. Next, similar to D was electric flux density. Similar to that, magnetic flux density is B. Okay, that is a vector. And so flux will be surface integral of B dot ds. Just like electric flux is equal to surface integral of D dot ds. So D and B are similar in electrostatics and magnetostatics. Similarly, H and E are similar. Okay, both are field intensities. So similar to D is equal to epsilon E, this relation is B is equal to mu into H. In electrostatics, epsilon is permittivity, whereas here mu is permeability. So there are some new terms and you can compare it with the corresponding terms in electrostatics. So electrostatics we learned flux density D, here it is B. Magnetic flux density is B. Similarly, electric field intensity was E, here magnetic field intensity will be H. Similar to total flux is surface integral of D dot ds, here it will be surface integral of B dot ds. Similarly, D is epsilon E, that is a relation in electrostatics. In magnetostatics, it will be B is equal to mu into H. And coming to one Maxwell's equation, the total magnetic flux through a closed surface must be 0, because you know that poles will not exist as a single pole. Like we can't separate north pole and south pole. So the net flux lines, if we draw, we can see that the net flux will be 0. So it's a common theorem that the total magnetic flux through a closed surface will be 0. So you can write psi is 0. Psi is equivalent to surface integral of B dot ds. So again surface integral of B dot ds will be 0. Again you can apply divergence theorem. You will get del dot B, volume integral will be 0, and from this you can learn del dot B is equal to 0. This is one Maxwell's equation. Del dot B is equal to 0. So from Gauss law you learn that del dot D is equal to rho, and here you learn del dot B is equal to 0. And now we'll go to Faraday's law. Faraday's law states that in any closed circuit, the induced EMF will be equal to time rate of change of magnetic flux linkage by the circuit. So, if you write in a mathematical form, induced EMF, VEMF will be equal to minus d psi by dt. Okay, negative of d psi by dt. Again, psi you know that it is surface integral of B dot ds. So V EMF, this you know earlier. Voltage and electric field are related like this. V EMF is equal to line integral of E dot dl. That is equal to what? This one, minus d by dt of surface integral of B dot ds. So you are trying to compare these two. On applying Stokes theorem, you can take LHS as surface integral of curl E dot ds. That will be equal to this. And you can write curl E is equal to minus dou B by dou t. So curl E is equal to minus dou B by dou t. This is one Maxwell's equation. This is derived from Faraday's law. Another term that you want to learn is displacement current density. So in case of Ampere circuit law, we concluded that curl H is equal to J. Okay. So when you take the divergence, del dot del cross H is equal to del dot J. You're taking divergence on both sides, and divergence of a curl of a vector will always be 0. Based on that, you should say that del dot J will be 0. But del dot J is equal to minus dou rho V by dou t in case of continuity of current equation. So here, according to this equation, we should say that del dot J is 0. But that is not true according to continuity of current equation. So you have to assume that to make this 0, you should assume that this J will be sum of two components. So you can take J as J plus JD, where JD is displacement current density. And when it is equated to 0, you can say del dot JD is equal to minus del dot J, that is dou rho V by dou t. So here you assume that del dot JD is equal to dou rho V by dou t. So you write like this, del dot JD is minus del dot J, and according to continuity of current equation, it is dou rho V by dou t. Again, rho V is substituted as del dot D. Okay. Again, you are comparing these two. You will get JD as JD, and here again del dot is coming. So JD can be written as dou D by dou t. JD will be dou D by dou t. Okay, so curl H is, instead of J, now you write curl H is J plus JD and substitute for JD. You will get curl H is J plus dou D by dou t, or J plus epsilon dou E by dou t. So this is another Maxwell's equation. Now we will learn all the four Maxwell's equations. This is the most important topic in applied electromagnetic theory, or the basics of electromagnetic theory. First one we derived from Gauss law, that is del dot D is equal to rho V. Second we derived from Faraday's law, that we learned just before. Curl E is equal to minus dou B by dou t. Then del dot B is equal to 0, and fourth one is curl H is equal to J plus dou D by dou t, or curl H is J plus epsilon dou E by dou t. You just have to learn the differential form. So these are the four Maxwell's equations. And another term is magnetic scalar potential. You know this relation in electrostatics, that is E is equal to minus del V, where V is potential and E is electric field intensity. So if you write something similar to magnetostatics, E corresponds to H. Similarly, H is equal to minus del Vm. If we can write like this, then V is the magnetic scalar potential. Then vector potential, magnetic vector potential can be related to flux density with this equation. B will be equal to curl A. A is magnetic vector potential. So you already know that magnetic flux is surface integral of B dot ds. On applying or substituting for B, you will get it is surface integral of curl A dot ds. On applying Stokes theorem, you can write it as line integral of A dot dl. So magnetic flux can be obtained by taking the line integral of magnetic vector potential. Okay, so Vm is the magnetic scalar potential and vector A will be magnetic vector potential.